Here we talk about Laplace transforms. So I plan to cover this topic in two sessions. The first session covers all the basics. There's the introduction of Laplace transforms, the basic properties of Laplace transforms, and the Laplace transforms of standard functions. At the end of the session, we will see how to solve a differential equation using Laplace transforms. The second session is dealing with more specific functions like the Dirac delta function and all, and some of the special addition properties of Laplace transforms also will be covered in the second session. Okay, so we'll start. So Laplace transforms is a very strong tool for solving differential equations. So by here we mean by differential equation we consider an initial value problem. That's a differential equation together with an initial condition, one or more initial conditions. So here the advantages, one of the advantages were the same method. This type of as the solution, this type of a method is applicable to many differential equations, and all differential equations are solved in the same method. The key point is that when you solve a first order differential equation, based on the category of the problem, the method of solution will be also different, like variable separable method, the homogeneous differential equations, etc. are solved with different tools. But here you can use the same method for all the differential equations, whichever is solvable using this method. Okay, now we see some general concepts about Laplace transforms. So it's a part of integral transforms. Integral transforms are basically converting a function f of t, there's a function of t, into another function capital F, which is a function of another variable s. So it's actually converting the function into another function, and the variable is also converted into another variable using integrals. For integral transforms we use the notation k. So k is a transform. Transform means it's a thing which transforms one object to another object. Okay, this k acting on f of t will give you a function of s. So how it is done is like this: you take the function f of t, multiply with a function k of s of t. That is, k is a function of two variables, s and t. This t has to be the same variable as that of the small f of t. Okay, then you integrate it from a to b, and the integration is with respect to t. So once you integrate it and evaluate at a and b, it's a definite integral. So when you evaluate it, the t will be evaluated at a and b, so that the t will be vanished, and what remains will be a function of s. So this k of st is called a kernel of the transformation, kernel of the transform, and depending on the kernel, the transforms are given various names. There is something called Fourier transform, sine transform, cosine transform, etc. And for Laplace transform, what we do is we take k of st as e raised to minus st, and the limits a and b are taken as a is taken as 0 and b is taken as infinity. So it's an improper integral. Now okay, first we see some basic things required for defining Laplace transforms. So you must be knowing about integration, and specifically improper integrals. Improper integrals means here we consider integrals with one of the endpoints at infinity. One or together both can be infinity when you deal with the Fourier transform, but here we consider integral from 0 to infinity always. So you should also know integration by parts. That is, integral of the product of two functions u and v is equal to the first function into integral of second function minus integral of the product of derivative of first function into integral of second function. And should also keep in mind that e raised to 0 is 1, e raised to infinity is the limit of e raised to x as x tends to infinity. So this is not a mathematically proper notation, e raised to infinity. By e raised to infinity we mean this, that's the limit of e raised to x as x tends to infinity. So it is, as you know, e raised to x becomes very large as x becomes very large, so the limit is going to be plus infinity. And e raised to minus infinity is the limit of e raised to minus x as x tends to infinity, so it will go to 1 by infinity, roughly speaking, so it is equal to 0. And you should also keep in mind that the polynomials, when multiplied with exponential functions, the exponential function will be always dominating. That is, even if p of x goes to infinity and e raised to minus x goes to 0, then the product will go to 0. So that's why we see that exponentials are always dominating over polynomials, or we also say that polynomial growth is smaller than the exponential growth. Okay, now we go to the definition. For a function f of t for t greater than or equal to 0, the Laplace of f of t is denoted as L of f of t, and it is defined as the improper integral 0 to infinity f of t into e raised to minus st dt, given that the improper integral converges. So the convergence is always not guaranteed, but whenever it converges, then only we will say that the Laplace is defined. Okay, we use the Laplace, as I said, it is a function of s, and for small f of t we will be using capital F of s as the Laplace transform. Now you can we will be following this notation. That's for any ordinary function, we use the small alphabet notation, that is small f of t for an ordinary function, and its Laplace transform is defined by or denoted by capital F of s, and g of t will be going to capital G of s under the Laplace transforms, and y of t will be going to capital Y of s under the Laplace transform. Okay, so this is how the definition goes. Now you can see some examples of standard functions. Now we see the Laplace of the constant function. Of course, you can take the constant function as 1, because any constant a can be written as a into 1, and later we see that the a can be taken out. Okay, that is for later. So Laplace of 1 is defined as integral 0 to infinity 1 into e raised to minus st dt. So that is you just integrate e raised to minus st. So when it is integrated, e raised to minus st by minus s will come. It has to be evaluated from 0 to infinity. Now when you evaluate at infinity, it becomes 0, and when you evaluate at 0, e raised to minus st will become 1. So it will be minus 1 by s into 0 minus 1, which is 1 by s. So it's very simple to evaluate the Laplace transform of constant functions. So even if it is a here, it will be just a into e raised to minus st, and a will come out. So it will be a by s when you apply the Laplace transform. Now the second example is of a polynomial. We take a first degree polynomial t. So Laplace of t is defined as integral 0 to infinity t into e raised to minus st dt, and you integrate it by parts. So first function is t, so t into integral of e raised to minus st is e raised to minus st divided by minus s. It has to be evaluated from 0 to infinity, minus integral of derivative of t is 1, and integral of e raised to minus st is e raised to minus st by minus s dt. And the first expression will completely become 0, because when you put infinity here, e raised to minus infinity will become 0 even though t becomes infinity. As I said, polynomials will be dominated by the exponential functions, and we put 0 here, then t becomes 0. T 0 into 1 it will become. So the first expression will give you always 0. This minus and this minus will get it will become a plus. So 1 by s into Laplace of 1. This what remains when you take this s out, what remains is integral 0 to infinity e raised to minus st dt. 1 into e raised to minus st dt, that is Laplace of 1. And that Laplace of 1 is 1 by s, which we have already seen here. So 1 by s into 1 by s will become 1 by s square. Now you see what happens when it is Laplace of t square, then this will become t square into e raised to minus st dt, and this will be t square here, and here it will be 2t. Okay, so this 2 will come out,